Greetings to the judges and viewers. Welcome to our innovation presentation for MJIC 2026. I am Tristan Chong Kok Ming from the Faculty of Applied Science and Technology at University Tun Hussein, Malaysia. Today, I am presenting our project, Fabrication of Silver Thin Film, Sputter Deposited on PET and Laser Annealing for Wearable Sensors Application. As we know, the future of healthcare lies in wearable monitoring system, devices that track our vitals continuously from the wrist or skin. In order to make this accessible, we need sensors that are highly conductive but also flexible. But the problem is that high quality metal films usually require high heat annealing to function, and standard thermal ovens often heat the entire device, which melts or deforms cheap plastic substrate like PET, and this limits mass production to expensive heat resistant materials. Therefore, our research solved this challenge with three key objectives, which first is to fabricate silver thin films on flexible PET substrate using sputtering, and second is to optimize the pulse laser annealing technique that treats the metal without damaging the plastic, and thirdly is to analyze the electrical and morphological improvement for use in strain sensing. Our methodology consists of three phases, where first is deposition phases. We use DC magnetron sputtering method to deposit a precise 27 nanometer layer of silver onto the PET substrate. And moving on is the laser annealing phases, where instead of using a slow oven, we use a 10,064 nanometer Nd:YAG laser. And by delivering rapid nanosecond pulses to the surface, we heat the surface instantly. And finally is the characterization, where we verify the result using SEM, AFM, UVB spectroscopy, and 4-point probe for morphological, optical, and electrical analysis respectively. Coming to our results and discussion, our results were significant. As shown in the electrical graph, the unannealed silver starts with a high resistivity of 4.46 times 10 to the power of -2 ohm meter. However, after laser annealing at 10 volts, this dropped drastically to 1.36 times 10 to the power of -4 ohm meter. This two order of magnitude drop confirm that the laser successfully recrystallized the silver. On the right, notice the significant drop in reflectance from the unannealed line down to the 8 volt sample. This confirms that the laser is actively modifying the surface structure, creating the roughness associated with grain formation. Moving on is our morphological analysis, where on the top row shows the unannealed samples. As seen in both the SEM on the left and the AFM on the right, the surface is smooth but lacks connectivity. However, the bottom row shows the optimized samples. Here we see significant grain growth and sintering. These larger conductive islands are exactly what created the high conductivity pathway we measured. The novelty of this project lies in the heating mechanism. Traditional thermal annealing uses global heating, which wastes energy and destroys flexible plastic. In contrast, our pulse laser annealing is selective. The laser energy absorbed only by the silver layer, leaving the PET substrate cool and intact. This allows us to bring high-performance metal to low-cost plastic. This innovation contributes three major benefits. First is cost effectiveness, where we unlock the use of PET, a cheap commodity plastic, eliminating the need for expensive high-temperature polymers. Next is energy efficiency. Our nanosecond process reduces annealing time from hours down to seconds. And lastly is high performance, where we achieve metal-grade conductivity while maintaining the flexibility required for wearables. The commercial potential is immense, directly supporting the rapid global expansion of the wearable technology sector. In healthcare, our solutions enable continuous, non-invasive vital tracking. This accessibility allows for early diagnosis and reliable home diagnostics without frequent hospital visits. In lifestyle, it provides a durable sensor designed for active motion, offering at least real-time biofeedback to optimize their performance. Currently, this research is being compiled for publication in the High Impact Material Science Journal. We are also in the process of filing for copyright protection regarding the specific optimization parameters of the laser scanning method. In conclusion, our project demonstrates that laser annealing is the key to fabricating high-quality flexible sensors on low-cost plastic. We are not just making thin films, we are enabling the next generation of accessible healthcare technology. Thank you.